So far, when we've looked at attention, we've been looking at a sequence-to-sequence transformation, where in the generating part of the sequence, we are attending to words in our initial sequence. Now, we're going to instead just look at a single sequence and look at perhaps a classification problem. So let's say we're looking at sentiment analysis for text. So we're going to have incoming T inputs. These might be indexes, let's say, into a dictionary. And so what we're going to do is we are going to not use an RNN. So instead, we are going to have a neural network that's large enough to fit whatever our largest sequence that we want to handle is going to be. And what we're going to do at each time, so we're not going to process things linearly, first the first one, then the second one, then the third one, and so on. Instead, we're going to work holistically. So we are going to say that we are going to calculate for every time step the context for that time step. That is, we are going to want to find, let's say for word 2, which of the other words is it interested in, right? Does it find useful in order to get some useful values? What about x1? We're going to do the same thing, attend to all the rest. xt is going to attend to all the rest as well. So instead of passing information from time step to time step, as we do in an RNN, instead, every time step can just look at every other time step to figure out useful information. So what we're going to do is basically calculate context 1, context 2, all the way to context of t. And we could then feed this in to a linear layer. So we can then take all these contexts, feed them into a small neural network, and compute our eventual softmax for our classification. So it's really fairly straightforward again. We are going to take our exabytes, and we're going to generate keys. We're going to also send in our exabytes and generate queries. And finally, we're going to send in our exabytes and generate values. Each three of these is going to be going through these weight matrices for keys, for queries, and for values. And then we're going to generate the contexts with, again, doing our softmax of our query times key transpose, and then we're going to multiply by our value. And that'll get us all our contexts. So rather than going time step by time step by time step by time step by time step, computing and updating our new h's, and only reflecting the information previous, we're instead going to allow, again, any of these contexts to depend on any of these other inputs. Now we do have this workaround with RNNs where we can do a bidirectional RNN, right? So where we can have, we're going from the left and going from the right. But there's no way, so really what we have is the forward direction RNN can look at all the previous values. So it can do computations based on everything it's seen so far from the left. And the other RNN can do everything based on the right. There's no computation that's actually looking at both of them together. And that's what we get to do here. Because for any of the contexts, we can look at any of the words that we want to. Let's look at a different problem. Let's say instead of classification, we had a language model, right? So if we had a language model, what we could do is feed this through a small neural network that comes out with a probability distribution across all words. And we could feed context 2 into, let's say, a neural network with shared weights. Okay, so these would all be shared. And we could do this all the way up to here. The key thing to note is let's look at a particular example of a sentence where we're trying to predict a missing word. Okay. So we've got two sentences. The trophy wouldn't fit in the suitcase because it was too big, or the trophy wouldn't fit in the suitcase because it was too small. Now let's say we want to know, for it here, which is it referring to? Is it referring to the trophy? Well, if the trophy wouldn't fit the suitcase because it was too big, it refers to the trophy. But if the trophy wouldn't fit the suitcase because it was too small, it refers to the suitcase. If we're trying to, let's say, generate a missing word here, our missing word is going to be it, and that's fine. However, if this is a problem in a different language, so let's say this is French, then trophy and suitcase may be of different genders. And so the it here is going to be different based on whether it is referring to the trophy or it is referring to the suitcase. And the context is what would be really useful, right? So we would want to have some information about what big and small, and that would tell us whether it is referring to the trophy or referring to the suitcase. So it's some difficult contextual information that we need, and we can get that with this self-attention. The basic idea of what we're going to be doing with a transformer network, the first idea of what we're going to do is actually we're not going to have a single layer of attention. Instead, we're going to have now, above this, we're going to have context 1 prime and context 2 prime, all the way to context T prime. So we are going to have another set of key, query, and value matrices that are going to apply to these contexts as input to the next level of contexts. And we can have however many levels of these that we need. And the idea is, just as if we have multi-level RNNs, that each layer is going from more concrete to more abstract information, the same thing is true here. We're going from the words themselves to some representation of the words, to a higher level abstraction, to a higher level abstraction, and so on. And we're representing that abstraction, however, in all of the contexts for all of the time steps, rather than in an RNN where we represent the abstraction as a single hidden state, or H and C if we have something like an LSTM. So we can get more and more abstractions here, and again, we're doing attention for all of it. We don't use any form of RN, we just use attention at each layer, up and up, so we're always attending to the previous layer.